In this video, we're going to be looking at monitoring energy consumption with the Flexs Q5. To monitor AC energy consumption, we need to monitor our load voltage and our load current. The analog inputs on the Flexs Q5 are only rated up to 60 volts, so we would need to use either an instrumentational transformer or what we supply is a Flexs Q5 high voltage reducer. So this module allows us to take in our line voltage on one side, and it's converted down to something that we can safely measure on this side. So we can connect that in there. And let's also go ahead and power up our device. Now we can log into our device. Come over here. We can see that our voltage is changing around a lot, 0.7, 4, and if we look at it on the onboard oscilloscope here, you can see we're picking up a sine wave, but we want to look at the RMS voltage because the sine wave or instantaneous voltage that we have here isn't super useful to us. So if we go over here under analog inputs, we'll see that there's a mode for RMS value. Additionally, there's also some scaling here we need to put in 1213, 0.142. Since our module's reducing the voltage, we need to adjust the scaling, and that's what this does here. So let's go ahead and test that. We can see we now are reading up correct voltage here, and that's a good start. This is an average voltage over a 1 second period, but what if we want to look at more information such as instantaneous voltage or frequency? To do that, we would need to use a power metric. So we can add a new power metric. 1, calculation mode, AC mode. Let's look at instantaneous voltage, average, min, max, and let's look at average THD and line frequency. Let's go ahead and apply that. Now if we look down here, we can see our frequency, 58 hertz. We have our instantaneous voltage, and we'll soon have our average, min, and max here. So we have 101 volts is our average, 103 is our max, and should have our min here very soon. 101 is our min. If we want this to go faster, right now it's calculated on a 10-second interval, so we could change that to a 1 second interval if we wanted those mins and max to be calculated quicker. And the instantaneous, min, and max, those are, whenever we calculate those AC values, we calculate those vectors, those power vectors on a single cycle, so that's, a single wave cycle. And so this happens 60 times a second. So the highest single cycle voltage would be the maximum. The lowest single cycle voltage would be your min, and then of course your instantaneous is constantly changing at 60 times a second, and the average is the average of all of those readings. And so that's good. We could clean this dashboard up a little bit. We could uncheck. We don't need to show all of the relay switches on there. And all of this data, the voltages, power consumption, power factors, this could be made available via SNMP, via Modbus TCP, via JSON, via RS-485, serial port. It could, whatever you want to do with this, do with that. This data is easily integrated with whichever platform you're using. So let's go ahead and uncheck these channels here. And for channels 1 and 2, we will keep those enabled, but let's just go ahead and not show any of these values. There we go. So we've cleaned this up a little bit. Actually, let's get that channel 6 off of there too. There we go. So now we just are showing one of the relay switches, and we're showing our power metric. And so if we wanted to actually measure line power, we would need to add in a current sensor. So right now we're just monitoring voltage. So what I've done is I've gone ahead and taken a power splitter and just exposed some of the leads here for a test. So we can plug this guy in right here, and then I have a current sensor. So this is just a clip-on AC current sensor. So there's lots of shapes and forms of these that come from lots of different suppliers. This one here is good up to 200 amps, so we can just clip that onto one of our wires. And let's just go ahead and route this into channel 2. Oops. Put that into channel 2. give us a little more space here. So now if we come over here to analog inputs, we can take channel 2, and this one says it's 0 to 200 amps corresponds to 0 to 3 volt output. So for channel 2, we can say 0 to 3 volts corresponds to 0 to 200 amps. And let's call this line current. And this will be line voltage. Now if we go back to our parametric, we can set, we already have our line voltage source. Let's just add our line current. You notice all of these then were enabled. So we can select instantaneous power, min max, and let's also do our power factor, and maybe our instantaneous amperage, and probably got our min max amperage. So just like the voltages, the min and maxes, the powers are calculated on a single cycle as well, which is super useful because if you have a big load starting, like a large air compressor or a large motor, you want to see those starting currents, even though if you're looking at, say, a 1 minute measurement interval, you're not going to see much change. But by being able to pick up those instantaneous values, we make sure we never miss any information. So now if we come back here, we can see there's pretty much no power consumption. We're looking at, milliwatts. So if we plug in, I have a test load here. If we plug in our test load, we'll see immediately 84, 85 watts. And if we turn this around, I'll change, so that'll be a positive now. So you can put this on either way. The direction that the power is going is going to determine if it's a positive or negative value. So this can also sense power direction. So you can pick up whether your power is going into your load or whether it's coming out of your load. So it's very useful functionality there. And if we look at our oscilloscope here, we can now see we have line current on there as well. And it's perfectly in line with the voltage because we basically have a resistive load here. It's pretty much a unity power factor. If we look here at a power factor, it's 0.99. So pretty much unity power factor. And yeah, so what we have here is this would all you need to do to get started with data logging. As soon as you have this here, you could log this to an SD card, or you could integrate the device with our cloud services. So this is another device that we've already gone ahead and integrated in with our cloud service. This is a 3-phase device. So we can look here, this is voltage, and so we can see voltage over time here. So the more solid line, that's the average, and then the maximum is the high, and the low is the low fill. So you can see these are some power surges when large loads were starting. So if we look, for example, right here, we can see some sort of large load was started. It had a peak consumption of 11 kilowatts, and then it ran there for a few minutes. And if we look up at the voltage at the same time, we can see there's also a low voltage recorded as well, under 94 volts. So it's super useful if you're trying to troubleshoot noisy power, any type of power interruption. Very, very useful functionality. You can see our phase B there as well, recorded the same kind of thing. So we can see it was a 3-phase load. It's reflected on each phase. So that's very interesting. You can see on this device as well, we can see what that looks like for the oscilloscope for 3-phase power. So you can see these are current waveforms, and the larger ones here, that's our voltage. And so it's just very much the same kind of setup. We have our voltage source, and we have our current source. And there's also, you could also do stuff with that data locally. So we could, for example, let's say we wanted to turn a load on when we want to activate one of the relays when, say, the load was above a certain threshold. We could do, again, programming is not required at all for strictly monitoring. If you want to do control, or you want to, say, add multiple loads together, do math on your loads, or calculations, these are options where your scripting can be super useful. So we could say if power metrics 0, again the first one, dot, actually let's do that, get extra information about it, dot real power, dot instantaneous. We could say it's greater than, for example, 50. We could set relay 1, true, else. So this would just turn that relay on or off anytime the power was above 50 watts. So we look back over here, you can see it's on. If I unplug the load, it's off. We can see that as well from here. It's pretty much instantaneous. As soon as I plug that in, that trips. So you could use that to, anytime the frequency was below a certain threshold, you could run a load or turn load off. A lot of people use it for load control and off-grid installations where they want to shed load below a certain frequency. Lots of flexibility you have there. And you could also, for example, we could make a web server. Maybe you want to make this data available to another application in your network. Of course, you have Modbus TCP, you've got SNMP, you have RS-485, you have a lot of built-in protocols for that, MQTT, but we could also just make a simple web server. We could say http.handle and make a request handler. So if we run this and we go to, whoops, put in the correct. So now we can see we've just created this web server that's returning all the data about that power metric. And so that you could also make that in a web request. You could send that object to your own web application, to your own server. You could also make your own request here. We could say power consumption 0.power. Do we make our own JSON object there? Make the request in our own format. As you can see now, we're just setting the power consumption. Lots of flexibility there. There's lots of built-in examples on how different parameters can be accessed. There's lots and lots of things you can do with that information once you have it. But the most useful functionality by far that our customers are really appreciating is just the energy metering, energy monitoring, being able to look at that power in such a real-time way. So we have a very high sample rate on these analog inputs, which allows us to pick up very instantaneous transient faults, which a lot of energy monitoring hardware solutions would completely just miss. And the analog inputs sample rate can be increased up to just several very high rates there, allow additional accuracy. You can see there we've just increased it to 16,000 times a second. It's very useful functionality to be able to examine your power quality, and there's a lot you can do with this. That's all on energy metering I had to share. If you have any questions, feel free to email us. Our website, FlexSCADA.com, our contact section. Feel free to reach out to us, and if there's anything that we missed or that we can help you with, feel free to let us know. Thanks a lot for watching.